But today I've been invited to talk, and my subject is a general question: could computers understand their own programs? To answer this question, I'll draw on two ideas that were originally put forward by ancient Greek philosophers, and on two ideas by Alan Turing, who I think is a great pioneer of computing science. In fact, one might almost date the foundation of computer science to, I think it's 1936, when he published his first paper on the subject, and I would suggest really founded it as an intellectual discipline. Well, I hope my answer to this question would have interested Alan Turing, and will also shed light on traditional philosophical questions about the nature of human understanding, its relationship to computer understanding, and the nature of the introspective self-awareness that we believe to be characteristic of the human race. I also hope my results will be eventually of use to designers and programmers and users of programs which control the computers, which are such a pervasive feature of modern life. Well, I expect it's usual in these cases for the speaker to tease the audience by making them wait until the end of the lecture to find out what the answer to the question is. But I thought I would summarize the answer briefly by saying yes, and then by giving some of the reasons for saying yes. The basic idea, due to Alan Turing, is that the understanding of computers can be tested in the same way as that of students, by an examination, preferably an interactive examination, in which the student is invited not only to give the answers, but also to explain and justify them. The computer will pass the test of understanding if their answers to their questions are considered to be useful by the person who most likely to ask the questions, namely the programmer who programmed the computer in the first place. It's notorious that that human beings don't understand their own programs very well, and they make a lot of mistakes. If the computer can show a better understanding of the programmer's program than the programmer does himself, I think that should be a reasonable pass mark for the examination that we're subjecting the computer to. Now, that leads me to, let's see now, the inspiration of the answers that I shall give you are due, as I said, to two ancient Greeks and to one Cambridge man, Alan Turing. He was at Cambridge at the time that he published his great paper on computing. Aristotle is the first of my sources. What I'm going to suggest is that when the computer has to justify answers about its own program to the programmer, the computer will be using logic, the principles of which were first, or attributed first, to the Greek philosopher Aristotle, and were further refined by the Egyptian geometer Euclid. But Alan Turing showed that these principles apply equally to reasoning about computer programs. And that's the summary of my argument. And the sources of my argument are Aristotle, Euclid, and Turing. I would recommend these websites if anybody is interested in pursuing the works of these great, the ancient Greek philosophers. They are eminently readable, and I found them extremely interesting, and I hope I will convey some of that interest to you in this lecture. Now, the ancient Greek philosopher Aristotle made a remarkable contribution to the history of human thought. He was the founder, director, and lecturer at a private academic institution to which he gave the name Academy, a name which is now applied much more widely to institutions of higher learning throughout the world. His lecture notes still survive. They deal with the sciences, the humanities, and he defined almost the full range of human intellectual endeavor for the next 2,000 years. I'll concentrate on his introduction to logic, of which he has a good claim to be the founding father. Now, why was he interested in logic, and why were his students interested in logic? Well, I think the possible explanation is that ancient Athens was a democracy in which the whole population of citizens, except of course women and slaves, assembled together and acted as the legislative parliament. There was no explicit party system. If any politician, or person who set himself up as a politician, wanted to pass legislation, he would have to persuade more than half his citizens to vote for the new law. Naturally, good powers of persuasion were essential, and what could be more persuasive than a logical argument? Equally important is the ability to refute the arguments put forward by your opponents. So it's no surprise, really, that the Academy and its rivals and competitors taught logic as a central skill and attracted many students thereby. Like all branches of science, the study of logic is defined by first listing the notation for a certain range of interesting concepts that constitute the subject matter of the science. The science then lists the range of sentences, predicates, or judgments which may appear in a line of a proof. Now, the definitions of these judgments are made by formalizing the grammar or the syntax of a greatly simplified language. Aristotle used the grammar of natural language to define the syntax of his logical sentences. Finally, he formalized the grammatical shape of each type of deductive step, the step which may validly appear in any chain of reasoning. Now, any argument which follows his grammatical rules is valid, and all other arguments are invalid. So the form of the syntactic definition that Aristotle used was rediscovered and extended by Chomsky in modern times, was developed by computer scientists for defining the grammar of programming languages. Aristotle introduced letters like S and P as non-terminal symbols, we call them, to stand for the subject and predicate of the sentence. These letters are intended to be replaced by universal names of sets or individuals, like sharks, fishes, animals, men. Aristotle's logic then permitted 4 forms of sentence which combine the subject and predicate using the words all, some, none, and not. Now, this summary here, the vowels A, E, I, and O were introduced later to designate these 4 forms of sentence. Aristotle then went on to define a set of 24 patterns of valid deduction, which are called syllogisms. Each syllogism consists of 3 sentences, usually written on successive lines. The first 2 sentences are called premises, major and minor, and they are written above the horizontal line, and the third sentence below the horizontal line is the conclusion of the syllogism. The purpose of the syllogism is to explain and check the validity of a very short argument, an argument which starts with agreement on the 2 premises above the horizontal line, and which ends rather rapidly with the conclusion on the third line, which the people who are reasoning in this way will agree is true as well. In this pattern shown here, the letters S and P stand for the subject and predicate of the conclusion. And the letter M, used in the premises, is called the middle term, and it is eliminated in the conclusion. This slide shows an example of a syllogism called Barbara. The three vowels A, A, A in the name Barbara indicate the syntactic form of the two premises and the conclusion of the syllogism. A second example is Celarent. The three lines of the syllogism are obviously of the form A, E, A, and E, as indicated by the vowels, and the conclusion follows fairly obviously from the two premises. Now, the purpose of formal logic is that you don't have to agree that once you've accepted the form of this argument, you don't have to use your intuition anymore to check that the argument is valid. You can just look at the form of the words, form of the sentences, and quote, if you want to quote anything, you say, Celarent, I know it well. And that was the purpose of formalizing the logic. The next example is, my last example is Darii. It's perhaps a little less obvious than the previous two examples. You can justify it by observing that from the second premise, that at least the S's that are in M must also be in P, because the first premise says that everything in M must be in P. And if you haven't followed that, then I've made my point, because you can now use this argument without really understanding why it's true. Here's a list of mnemonics, if you can read fast enough, for all the 24 syllogisms of Aristotle. They are, in fact, a complete list of all the valid three-line arguments that you can make in logic, which can be written in Aristotle's Aristotle's syntactic form. In earlier times in universities, students of logic would know all of these names and be able to recognize them and use them in disputations with other students and with their examiners. Fortunately, I'm sure you'll be glad to hear, modern logics have greatly simplified the study since Aristotle's day, and at the same time they are now much more powerful. For example, the simplest branch of logic, propositional calculus, or Boolean logic, which is, as you know, nowadays used in the design of every digital computer, can be based on just a single deductive rule instead of 24, and a few simple and obvious axioms. Now, the example deductions shown on this slide are taken from Aristotle's classificatory biology, because in addition to being the founding father of logic, he's also founding father of biology. His study of biology dates from a visit that he made to the Greek island of Lesbos, where he got the fishermen on return from a fishing trip in the morning to show and name for him the various kinds of catch in their nets. He realized that sharks and rays were similar to each other, but different from the majority of the fishes and the inhabitants of the sea. So he classified these two species under a distinct genus of Selachians. Now, the intention of Aristotelian logic is not just to validate three-line proofs, but proofs of any length whatsoever, which can be obtained by chaining together a number of little three-line proofs. Here's an example of a five-line proof containing one instance of Barbara and one instance of Darii, and the middle line of this five is the conclusion of the first syllogism, the Barbara, and one of the premises of the second syllogism. Following this pattern, Aristotle, he didn't use this definition, but it enables me to describe. You can define a proof syntactically using the techniques of Chomsky in the following way. A proof is a series of lines in which every line is either itself a premise or it is the conclusion of a syllogism, one of the 24, a conclusion from one of the two, from two of the premises that precede it in the proof. In other words, when you use a syllogism, the premises of that syllogism must appear in the same proof earlier than the conclusion. And if that ordering is preserved, you won't get any cyclic arguments, and no matter how long the proof is, it will still be valid according to Aristotelian reasoning. And this is the definition of a proof that we still use today. Now, Aristotle realized that his logic was a completely general purpose or universal tool, just as we realize that stored program computers are general purpose tools in the present day. And the reason for this is because the validity of a proof depends only on its syntactic form and in no way depends upon its subject matter. You don't have to know what it was all about. You do not have to know whether the premises are true. You do not have to know whether the conclusion is useful. And this goes against all of what one would, the views that one would attribute to the ordinary man in the street, even in ancient Athens. The validity of our argument depends most of all on whether you want the conclusion to be true or not. After that, it may depend on whether you like the person who's making the argument or not. And after that, perhaps the most reasonable thing is to say that it depends on whether the premises of the argument are true or not. What Aristotle realizes is it doesn't depend on any of those things at all. It's because it doesn't depend on any knowledge of anything outside the form of the argument itself that computers are so good at understanding proofs. Computers can check proofs and even to a limited extent at the moment construct proofs purely by looking at their syntactic form and not understanding in any way how they are applied or to what part of the real world they belong. Now computers, the great advantage of using computers in the conducting of proofs is that computers can examine far more cases than a human being would have the patience or the accuracy to enumerate. Computers have recently been helped in generating and checking long proofs of interesting theorems in mathematics, and they have established conjectures that were made centuries ago by great mathematicians in the past and which mere humans have been unable to solve without computer assistance until late in the last century. Recent notable examples are the famous four-color theorem and the Kepler conjecture. So let's have a look at those. The four-color theorem tells us that a map of the constituent states of a country, every state can be painted in one of four colors in such a way that no two neighboring states that share a border need also share a color. So every border is clearly visible by having different colors on both sides of it. You don't need to draw the line between them. Here's a little extract from a well-known map. And the left-hand example shows that you do actually need four colors to color that map. The three states around the square green state have all got to have different colors from green, and they must all have different colors from each other because three states in a ring obviously require three different colors to establish the differentiation. Now, but is 4 colours enough? Well, perhaps some more complicated graphs would require more colours, and that has only recently been proved to be unnecessary, to be false. Supposing we make the map a little bit more complicated by asking Texas to cut itself in half. I don't think they would actually do it, but if they did, they'd actually make the job easier, because the additional state around the circumference means we can get away with just 3 colours. Now, this was proved partly manually and partly by computer assistance in the last century, and recently a new proof has been given of the whole theorem, including the manual part, the bit that was supplied by humans, by my colleague Georges Gontier, and he validated the proof using the Coq programming language and proof validating system. So the computer has actually checked that proof. His proof was much simpler than the original proof. He had to invent a whole new branch of mathematics, a new branch of digital topology in order to do it. It required examination of 633 cases, as opposed to 2,000 cases or so originally. And each case required around 1 million proof steps, very small proof steps. So we've got approximately 1 billion steps in all, way beyond human comprehension. And it's the shortest known, obviously, completely formal proof. It's the only completely formal proof so far. It was actually, of course, a computer program that generated all those steps and which sequenced through all the cases. That was not done by Georges or anybody else. Now, the Kepler conjecture is sort of equally intuitive, and it similarly resisted human attack for many years. It tells us the best way to pack a lot of oranges in a large but limited space is the way that costermongers and greengrocers have done it for many years, by allowing them to settle all together in rows. Now, a computer-assisted proof of this was discovered in 1998 by Tom Hales, and a fully automatic proof of the Kepler conjecture is still being investigated. It hasn't been accomplished yet, and it's estimated that it will take a further 66 man-years of mathematical effort to get the computer to recognize this as a valid proof. What have we got here? I'd like to now introduce my second Greek thinker, Euclid. He worked in Alexandria about 300 BC, really only 50 years after Aristotle. And he systematically applied logical deduction to the proof of theorems about physical space, with applications to the measurement of land, which was, of course, the original meaning of the word geometry, measurement of land. Maybe it wasn't surprising that geometry flourished in Egypt, because Egypt has quite a significant land measurement problem after the rising of the Nile has wiped out all the previous boundaries. They will need to be redrawn. That's a rather fanciful speculation of why geometry appeared first in Egypt. But of course, Euclid's geometry applies to many other things besides drawing pictures in sand or putting up boundary fences. It applies nowadays to the design of buildings, to the surveying of land and sea, to the making of maps and charts, and indeed to the display of diagrams on screens of computers and television sets and cinemas today. Perhaps one could also mention that his textbook on geometry has been the basis of mathematical education in Europe and Arab Middle Eastern countries for upward of 2,000 years. Now, if you're ever asked to measure your own impact, I think is the word people use today, I would advise you not to use Euclid as a measuring stick. Now, the logic of Euclid was very different from that of Aristotle. It didn't reason just about facts. Rather, it reasoned about actions and showed how to prove that actions and series of actions had some desired effect that you wished to achieve by carrying out those actions. The major part of a typical Euclidean proof is a construction, a program of actions which will draw a line or a triangle or other figure which possesses some desired property. And the rest of the proof just proves that it does so. Euclid therefore gives a comprehensive set of rules for reasoning about his programs or constructions. He demonstrated the use of his rules in the proof of hundreds of geometric theorems. So I would call Euclid the inventor of the world's first programming language. It's similar to a modern graphics programming language used to draw geometric pictures on our screens and televisions and touch screens. It contains many of the essential features of all of the languages we teach and use today in introductory courses for computer scientists. Of course, Euclid's programs had to be carried out by people, using only instruments available, shall we say, to land surveyors of Euclid's own day, perhaps pegs and strings for marking out boundaries in the land when the annual flood has receded. So perhaps it's not surprising that the formalization of geometry was achieved in Egypt. Now, Euclid defines his programming language in 5 basic axioms or postulates. They actually are not stated as sentences or descriptive sentences. They are actually describing the basic actions which are performed in Euclidean constructions. For example, the first postulate allows the program to draw a straight line between any 2 points which are given as parameters to the action. The third postulate is an action that draws a circle with a center at a given point, and the second given point on its circumference. The famous fifth postulate allows the drawing of a line parallel to a given line and passing through a given point. These basic actions are included in all graphics programming languages today. Now, with any luck, I have a little animation which illustrates the action of postulate 3. No. There we are. Well done. Thank you. Now I think I can go on to the next one. The postulate's accompanied by some 23 definitions. Some of the definitions, like the first one, a point is that which has no part, sort of relates the words of a language informally to their meaning in the real world. Other definitions, like number 20 shown here, define new words in terms of previously defined words. Definitions 15 and 16 state that a circle is a figure in which every point on the circumference is the same distance from the center. And as a result, every radius of the same circle is equal in length to every other radius. How many of you studied Euclidean geometry at school? Oh, great. Might be able to go a little bit faster. Here's a picture that illustrates Euclid's definition of an equilateral triangle. The picture introduces a modern convention that equal lines in a diagram can be decorated by the same marking, for example, a yellow twiddle. And here I've used the same marking convention to summarize Euclid's definition of a circle. He defines it as a figure which has all points on its boundary at an equal distance from the same point, namely its center. Now, Euclid realized that geometry was only a particular application of a more general principles of logical reasoning, which he called common notions. They relate to mathematical and logical concept of equality, and they're built into all systems of modern mathematical logic. Now, the main part of Book 1 of Euclid's Elements is a collection of 48 theorems, usually called propositions. The last two propositions, 47 and 48, are the well-known theorem of Pythagoras. And the first proposition is one that constructs an equilateral triangle and proves that it satisfies the definition. Number 20. Now, the purpose of a proposition is like that of a subroutine or function or method in a modern programming language. Just like a subroutine in a program, it can be called by its name or its number as a single command in any subsequent proof. The call will perform the construction described in the proof of the called proposition. And then the proven property of the construction can be used in the proof of the calling proposition in complete confidence that the constructed figure will have that property. It's been proved. Confidence is based on a valid proof in the logic of geometry as defined by Euclid. So I think Euclid was not only the first person to design a programming language, he also designed it by principles that really appeal to my heart. He designed it as a language in which every program can be proved correct. I revived this idea in 1969 in my first paper on Hoare logic, as it was later called, and thought that it was a long time in the future before anybody would design a language in which you could prove every program correct. And I think I didn't realize that Euclid, whom I did study in school, had already done it. We must do it again sometime. Right, have I got? To construct an equilateral triangle with a given line as one of its sides. Now, how many of the people who studied Euclid remember how to do that? Great. Well, just in case. First of all, you have to choose one of the ends of the line. That's very important. It's a sort of axiom of choice which he didn't really make explicit. So let's just choose one end, and then we'll draw a circle around that end, using postulate 3 to justify the construction, and then around the other end as well. Now, it's becoming rather more obvious. We have to choose a point C. Now, Euclid didn't, I think, quite realize that this is quite a major step, because first of all, he didn't actually prove that the two circles would intersect. And I don't think it's altogether trivial to prove that when the centers of two lines are close enough, they will meet in 2 points. Anyway, the second point, C, which he could have chosen, which makes his construction non-deterministic, in the sense that we understand nowadays for computer programming when we write non-deterministic programs, which most of us very often do. Then choose the point on the line, and using postulate 1, draw a line between them. We could do the same thing a second time, and then we can start our proof. We'll claim that those 3 lines that we've just drawn on top of the given line, 2 lines that we've drawn on top, constitute an equilateral triangle. And we start the proof by noting that the 2 lines marked equal are the radii of the left-hand circle, and therefore they're equal to each other. Similarly, the 2 lines on the right. And finally, using the common notion, 2 things that are equal to the same thing are equal to each other, we can deduce that the other 2 lines, the yellow twiddle lines, are all equal to each other. Lovely. And using the definition of equilateral, well, all these steps have been made very explicit. I've gone through them very slowly, and I've justified each one of them by appealing to one of Euclid's very few axioms. And that's what a computer does when the computer checks a proof or generates it. So in his next theorem, he actually uses this construction to prove, I've forgotten what, but you certainly didn't have to repeat the construction in order to prove the second theorem. So, what does Euclid's language consist of? Primitives, primitive actions, a definition of new names. Let C be a point on. This is like an assignment. But it was only a single assignment language. You couldn't redefine C again in the same proposition. Sequencing of commands. First of all, draw one thing, then draw another. Subroutines, I've talked about. Draw an equilateral triangle. Preconditions. The performance of a construction depends on what is given to it, given the straight line. And postconditions are the result of the construction stated categorically that the triangle is equilateral. He doesn't have conditionals, and he doesn't have loops. So those are really rather important features of modern languages which he doesn't deal with. So can I come on to Alan Turing, he was recently celebrated his centenary year, and he's made contributions, a bit of a polymath like Aristotle, in number theory, developmental biology, statistics, philosophy, cryptography, logic, and of course computer science. And these are not trivial articles. They can still be read with illumination and referred to and used today. So these are the what Alan Turing provided, the evidence that I shall give for a positive answer to my question. He invented a logic for reasoning about programs. He knew that a computer can use any logic, particularly this one, to answer questions about its own programs and to justify its answers by proof. So I'm not going to tell you about the way in which Turing presented his results, which were then rediscovered many times. John von Neumann knew that programs could be verified by proof. It was rediscovered again by Peter Nauer and by Bob Floyd. And I got the idea from Bob Floyd and just invented a new notation for it, which is a terribly unfair thing to do, because everybody knows my notation and people forget Bob Floyd. It was his idea when I read it, but as I say, Turing was the first. But I will explain his logic using my notations. Well, I won't use my notation, that is my notation, but what it means. When P is true, an action V ensures that R is true afterwards. So V is a verb which changes a part of the world, perhaps, either inside or outside the computer. P describes an initial state of that part of the world, and R describes the final state resulting from the action V. Here are a few obvious examples. When the radio whistles, turning the suppression knob clockwise ensures the absence of the whistle. The theorem proved by Euclid is the second example, and the third example is taken from ordinary programming. If the value of a program variable x is greater than 3, increasing the value of x ensures that it's greater than 4. Very trivial examples. So now let's look at the way in which one can put these sentences together to prove the correctness of larger actions consisting of many components, each of which is an action. And let's draw these like the syllogisms of Aristotle, with two premises and one conclusion. So if we prove the premise that when P is true beforehand, V1 ensures S. S is a sort of middle term here. It appears in the two premises, but not in the conclusion. Second premise, when S is true beforehand, V2 ensures R. And so when P is true beforehand, the action of doing V1 and then V2 ensures R, because S now denotes a step in the progress of the computation in between the P and the R. So the next one, I think, fills a deficiency of Euclid's standard reasoning. It reasons about conditionals, where we make the action conditional upon the initial state of the, let's call it a computer, state of the world. When P and B are true together, then V1 will ensure R. That's my first premise. Second premise is that when P is true beforehand and B is not true, then V2 ensures R. If R is what we want, then clearly we should look and see if B is true. If it's true, we'll do V1, and if it's false, we'll do V2. But that's what's said in the third line. When P is true to start with, test B. And if B is true, do V1, and if B is false, do V2. And as a result, whichever one you chose is going to ensure R. And that's been proved by the two premises. Repetition, a loop that you carry out many times, can be proved by this rule. When P is true and B is not true, supposing the action V will restore the truth of P. So what we want to do is to, so the second time we come to perform V, we will be able to use the first premise again. And so after doing it twice, P will still be true, and after doing it any number of times, P will still be true. Every time that we finished V, we test whether B is true and hope very much that one of those times B will in fact be true, and then we'll get home for dinner that night. We'll achieve are. Very long shaggy dog story, really. Non-determinism. Perhaps I'll just... Non-determinism. We saw non-determinism in a Euclidean proof, where there were two ways of choosing a point C, and the rest of the proof didn't matter which choice you had made. That idea is incorporated in this rule, where we have two actions, V1 and V2, and both of them will get us where we want to be. If we can prove that both of them achieve the result R, then we can allow a non-deterministic choice, a V1 or else V2, without saying that why one should be chosen rather than the other, leaving it completely non-deterministic. That choice, whichever one is chosen, will in fact achieve R. And that's been proved in the first two premises of this rule. Now, the final step in my argument is that the computer is also due to Turing. The question of how do we test the understanding of a computer? He published it in the British philosophical journal Mind. I expect you all know the Turing test. If you recall, it's just a sort of cultured small talk between a man in the street and a computer, and the man in the street is, after 5 minutes of a conversation, which may range over any subject whatsoever, the man in the street has to decide whether he or she has been talking to a computer or to a real person. And if the man in the street doesn't get significantly better than chance results from that encounter, then the computer has passed the test. It's a carefully designed test. 5 minutes you've got to choose, and people have been trying to pass this test, and they've been offering $1 million prizes for the first one to pass the test, and nobody's managed to get anywhere near it. There was one of the recent competitions that they had to try and pass the test did produce an interesting positive result, that one of the human contestants, the person who was playing the part of the computer on the other side of the wall, actually thought it was that he was being asked to behave like a computer. And he won the test. Everybody thought he was the computer. So, I want to propose a test which is is rather more specific than that, and which still is way beyond the reach of the current state of the art. I suggest that we should test the computer. First of all, we will restrict the subject matter of the examination to computer programs. We won't expect the computer to know the poems of the sonnets of Shakespeare, which Turing thought the computer would one day be able to understand. So the single topic of its own program, and we won't put any time limit on. 5-minute time limit is actually quite short. The criterion of understanding is that the machine gives the answer to most questions. We don't require it to answer all questions, because we know that there are some questions that cannot be answered without contradiction. And Turing, of course, is responsible for discovering that. But the real criterion is that the examinee can explain the reasoning behind the answers. So if the human being can't understand the answer, or doesn't believe it, and wants to know why that answer is true and relevant, you can ask a supplementary question of the computer. Most of the answers should be relevant and useful. Some of them will be way up the wall. Anybody who's acted as an examiner know perfectly well that the examinee doesn't have to answer all the questions, nor indeed do they have to justify all parts of their answer, nor indeed do they all have to be correct. So we should at least afford the same license of error to our computer programs. So, typical questions that we might like to ask. Can your program overflow a buffer? It was a very interesting question for Microsoft at one time. Now, my friend and colleague Jay Moore at University of Texas at Austin put forward a view of perhaps 50 years in the future that a design automation system, we want to use this capability of a computer to understand its own programs, to get the computer to help us to write the programs and to get them correct. And Jay Moore hopes that in 50 years there will be such a system which will be widely used by software engineers in all stages of the design of a program, analysis, design, programming, testing, delivery, and subsequent improvements, very important, because most programs these days are actually just small changes to existing programs. And that this tool will be used in order to save money that would otherwise be spent in writing these programs, in order to make the process of controlling and programming computers easier, cheaper, more flexible and quicker. And until that is true, we can't expect engineers to use the tool, and when it is true, they will use the tool anyway, whether we expect it or not. So, the picture I would like to paint is a sort of collaborative program development between the human programmer and the computer. The programs of the future, each of these parties will contribute their own particular skills. The human being has common sense. Human has a common sense understanding of the real world, which the computer really does not. Human has an intuitive understanding of the needs of the people who will be using the program. Human being can make a good guess about the possible commercial value of the software product. But above all, the human being can take responsibility for the consequences of the use of that program, and the computer cannot. And it's that that makes us believe the human being in distinction from the computer. However, the computer can contribute an accurate understanding of the wealth of important detail that is needed in a modern, sophisticated computer program. And what's more, we hope that it will be able to predict the consequences accurately, the consequences of changing the program even after the program has been delivered. And what will happen in the end? The software engineer will complain. They will say, well, the computer's only doing the easy part of the task. The computer doesn't understand what I want to do. Of course not, the computer doesn't understand. Oh, why did he use the word understand? Sometimes the computer understands, sometimes it doesn't. I mean, maybe it understands ordinary sorting programs, but it doesn't understand complex arithmetic. And there is the answer to my question. We're already naturally using the word understand to describe the response of the computer to the questions that we ask it. And we sometimes wonder, oh, did the computer understand what I was trying to do? The answer to that is very nearly always no. I didn't tell it, and therefore it doesn't understand it. And the fact that it doesn't understand it makes it possible to understand what it does understand. That's a very important criteria. So I'll claim that computers can understand by an analogy with human understanding in the same way that aeroplanes fly. by analogy with the flight of birds. They don't flap their wings, they don't lay eggs, but we do say they fly. And it's a very good analogy, and nobody worries about it at all. But why don't submarines swim? It's just a question of idiom. When I was giving a lecture based on this one in Warsaw the other day, I was told that in Polish submarines do swim. So, on that, let me end by quoting Alan Turing, which roughly speaking describes my own life's work. The language in which one communicates with these machines forms a sort of symbolic logic. Thank you very much.
Okay, on that fantastic note, Tony, could I say thank you ever so much for such a brilliant, philosophical, insightful, inspiring, and special lecture. And could I present you with a couple of things? First of all, a very special certificate commemorating this lecture, the Wheeler Lecture, and also the about to be published in 15 minutes, very special book on Cambridge computing.
Oh, lovely.
So thank you ever so much. Thank you very much.